Pre-stressing steel. The development of pre-stressed concrete was influenced by the invention of high-strength steel. It is an alloy of iron, carbon, manganese and optional materials. Forms of pre-stressing steel: wires, strands, tendons, cables, bars. Types of pre-stressing steel. The steel is treated to achieve the desired properties. The following are the treatment processes: cold working, stress relieving, strain tempering for low relaxation. Properties of pre-stressing steel: high strength, adequate ductility, bending ability which is required at the halving points and near the anchorage, high bond required for pre-tensioned members, low relaxation to reduce losses, minimum corrosion. Stiffness of pre-stressing steel. The stiffness of pre-stressing steel is given by initial modulus of elasticity. The modulus of elasticity depends on the form of pre-stressing steel. Allowable pre-stressing steel. The maximum tensile stress during pre-stressing shall not exceed 80% of its characteristic strength. There is no upper limit for the stress at transfer or for the effective pre-stress. Post-tensioning equipments: casting bed, mold or shuttering, ducts, anchorage devices, jacks, couplers, grouting equipment. Structural behavior. Effects of pre-stress. The act of pre-stressing causes the floor to bend, shorten, deflect and rotate. When any of the above actions are resisted, secondary moments are set up. If the level of pre-stress does not exceed 2 Newton per mm square, the secondary effects due to the restraint in the shortening are neglected. Flexure in flat slabs. Flat slabs are those floors which can carry loads in two different directions to discrete column supports. A flat slab supported on columns rather than perimeter beams can fail as a one-way mechanism just as a single-way slab, and it should be reinforced to resist the movement from the full load in each orthogonal direction. Typical flat slabs. The effect of tendons are most critical since they exert loads on the slab and provide reinforcement. Since the tendon effect is opposite to the effect of gravity, the net load causing bending is reduced. An additional effect of the tendons is the axial precompression, which counteracts flexure tensile stresses. The load balancing technique. By the balanced load approach, the attention is focused on the loads exerted on the floor by the tendons perpendicular to the plane of the floor. A look at a plan view of a flat slab reveals that columns provide an upward reaction for only a very small area, which is supposed to provide the upward uniformly distributed load. So a second set of tendons must be provided perpendicular to the first to provide an upward load to resist the downward load from the first set. Flat slab criteria. Pre-compression should be applied in two orthogonal directions. The pre-compression at the edges of the slab is concentrated behind the anchorages and spreads into the floor with increasing distance from the edge. Past experience has proven that for the pre-compression to be effective, it should be at least 0.7 Newton per mm square in each direction. Aspect ratio, that is length to width ratio of any panel, should not be greater than 2. The ratio of stiffness of the slab in two orthogonal directions should not be disproportionate. Losses in pre-stress. In pre-stressed concrete applications, the most important variable is the pre-stressing force. In the early days, it was observed that the pre-stressing force does not stay constant but reduces with time. The losses are broadly classified into two groups: immediate, time dependent. The immediate losses occur during the pre-stressing of the tendons and the transfer of pre-stress to the concrete member. The time-dependent losses occur during the service life of the pre-stressed member. The losses due to elastic shortening of the member, friction at the tendon concrete interface and slip of the anchorage are the immediate losses. The losses due to the shrinkage and creep of the concrete and relaxation of the steel are the time-dependent losses. Figure represents the classification of losses. Construction of a pre-stressed concrete structure. Over to Divya.
Pre-stressed concrete, being ideally suited for larger spans, is having very few applications when it comes to substructures than for superstructures. It is mainly used for building the load-bearing components. Rapid development in construction techniques of pre-stressed concrete structures over the last few decades has resulted in several novel methods of construction. Before starting the construction of any pre-stressed concrete structure, it is important to consider the minimum requirements for material and workmanship which will result in a structure that will perform satisfactorily in various limit states. The most important consideration, however, of pre-stressed concrete structure is the design, production and control, that is the quality control at field mainly of high strength concrete with desirable properties. Maintenance and rehabilitation. Just like post-tension slabs are an advanced technique, it requires maintenance and rehabilitation also. One of the primary reasons being it's a much different from the traditional reinforced concrete construction method. The fundamental objective of maintenance management of pre-stressed concrete structures is in such a way that it will function satisfactorily at various limit states, maybe the ultimate limit state or the serviceability limit state, immediately after construction and also over a period covering the lifespan of the structure. Good maintenance practice requires periodical surveillance, identification of local damage, deterioration and loss of durability of the structure due to environmental and other load effects. The overall objective of the maintenance of pre-stressed concrete structures is to identify the need for structural integrity, periodical surveillance, repairs, rehabilitation and replacement depending upon the local conditions. Maintenance is one of the prime reasons for the healthy condition of the structure. Inspection. Inspection is carried out in three ways. It may be a routine inspection, detailed inspection or special inspection. These are the following inspection instruments. Rebound hammer. This is used to check the strength, compressive strength of the material. Ultrasonic pulse velocity. This is mainly to test how strongly and how well the material will withstand. Snooper, magnetic detector, mechanical extensometer. These are all again used for checking strength and the durability of the structure. Hydraulic jacks. These are used for the pre-stressing purpose. Electronic strain gauges, vibration measuring equipment, electric resistant meter. Site details. The proposed construction is a commercial complex for Ekta builders with an area of 70,000 square feet. Is a building of the type 2 basements plus G plus 5 floors. Maximum span allowed is 40 inches. It's a flat slab system with a live load of 4 kN per meter square and standard dead load of 2 kN per meter square. The design process. Generally, a design process consists of 4 steps. Preliminary design. Check the design by analysis. Revise the design if the obtained values exceed the limited values. Repeat steps 2 and 3 until you get a favorable design. Step 1. Structural layout. Column layout means positioning the columns according to the distribution